When you've got through the long years of university training, and you've got your PhD, and you're a real scientist, how should you start to tackle your first problem? Well, I think a very useful thing to do is to challenge the dogma, the conventional wisdom that your colleagues around you tell you is the basis of the science of the problem you're working on. Challenging conventional wisdom is the way to make waves in science. And let me give you a very simple example. When I first went to work for the Medical Research Council in 1941, one of the problems we had was, how do aerial disinfectants work? The reason we were interested, there was great fear there would be influenza epidemics under the packed conditions of tube shelters in London during wartime, and they used to go around spraying the air with aerial disinfectants to kill any airborne organisms that were present. And one of the problems was, how do they work and can we make better ones? And the conventional wisdom was that the organisms were killed by droplets of the disinfectant floating in the air colliding with them. Well, for some reason this seemed to me very dubious. I thought, I don't believe it, doesn't make sense. And I did the sums, and it soon came out that, knowing how many disinfectant particles and how many bacteria were floating in the air, that it would take days, if not weeks, for collisions to occur. And yet we knew from experiments that the organisms were killed in seconds, or at the most minutes, so something different was happening. What? And with a few fairly simple experiments, I was able to show that the organisms were killed by the vapor of the disinfectant distilling over from the disinfectant droplets onto the bacteria and thereby killing them. And with that knowledge, I was able to invent very much more effective aerial disinfectants that were very much more toxic to organisms and less toxic to people. In fact, the best one turned out to be simply lactic acid, which is a natural component in your body, but if you vaporize it in the air, it kills organisms faster than anything. And so that's challenging the conventional wisdom. And of course, that has been my pitch throughout most of my lifetime. When I was working on freezing, nature freezing damage, the conventional wisdom was that cells or tissues or whole animals are damaged when they're frozen by the ice crystals penetrating the cells and sort of mechanically breaking them up. Indeed, they had film showing this happening on a microscope, freezing microscope slide of the ice crystals penetrating the cell. It all seemed very real. And being my usual skeptical self, I thought, I wonder if this is true. And I imagined myself, a cell, being frozen. I thought, what happens? Well, water's going to, when it starts forming ice crystals, it'll form small ones at first, which shouldn't be too intrusive, but it's going to separate as a pure substance. It always does. Ice is pure water. So what happens to the things that are left behind? Cells float in a slightly salt solution. The salt would become concentrated. And quite rapidly it became clear to me that in no time in freezing, the salt concentration would rise to the level of pure brine. At -20, it's 5 molar. 5 is, saturated salt. And this kills all cells very rapidly. And a few experiments demonstrated that you could account for virtually all of the damage that occurred to living cells when they were frozen under the conditions that my colleagues were freezing, which is slow freezing, by the concentrating of the salts in the solution. The ice crystals had nothing whatever to do with it. And this led in practice to the invention of better antifreeze agents to prevent it. And one of them was dimethyl sulfoxide, which has been used in freezing eggs and things for keeping them, human eggs, for keeping them for long term, for fertilization procedures, and so on. And of course, in the work I did on the self-regulating Earth, the Gaia theory, the great conventional wisdom of biology and of geology, come to that, is that organisms adapt to their environment. That is the great dogma of the subject. Well, it's something to think about. It assumes that the environment is a given. determined by the chaps who work in the other building of the university, the geologists, not by the biologists. The geologists, of course, assume that the biology does nothing to their evolution of the rocks, that the two processes are quite separate. And a way to look on Gaia theory is that it's a new theory of evolution, which sees the evolution of the organisms and the evolution of the earth, the rocks, the air and the ocean, not as separate processes, but as two tightly coupled processes evolving together. You see, everything alive changes the environment. You can't help it. When you breathe out carbon dioxide, you're changing the atmosphere. When you breathe in oxygen, you're taking the oxygen away. Just but two examples. Everything is alive is influencing its environment. So we are not evolving in a geological given, we're evolving in a world that our ancestors have made. You could say that we're evolving in a world which is made of the breath, the bones and the blood of those that went before us. And this comes from challenging the dogma that things just adapt to that earth that's there, a given.